All right, great. So next up we have Alex, who's going to be telling us about on learning polynomial recursive programs. Take it away, Alex.
Okay, hello everyone. This is a joint work with Vincent Cheval, Mahsa, Shirmohammadi, and James Worrell. And first I want to start by describing what I mean by learning. And the framework that I will be using is Angluin's minimally adequate teacher. And what does this involve? So let's say that we have a program like the one you can see on the left, and we don't know the context. So imagine it's a black box, and I will call it an unknown target, which maps strings to rational numbers. And we would like to find out what is in the black box, and we have access to a teacher, which basically consists of two oracles. The first oracle is a membership query oracle, to which we can ask what's the value of a certain input W. And we have an equivalence oracle to which we pass a hypothesis, something which we think might be in the black box, and the teacher will tell us if they're equivalent, in which case we halt. Otherwise, the teacher will provide us with a counterexample, by which I mean just the word on which the hypothesis and the target function disagree. Next, I will talk about something which seems a bit unrelated at the moment. So I will talk about sequences, and I'll just give you two examples of probably very well-known sequences: the Fibonacci sequence and the number of involutions. And an involution is simply a self-inverse permutation. And the first thing to note is that the second sequence, the number of involutions, grows a lot faster than the first sequence. And this can be intuitively explained by looking at the recurrence relation they satisfy. So for the Fibonacci sequence, Fn is equal to the sum of the previous two terms, whereas for the number of involutions, it's In is equal to the previous term plus n minus 1 times In minus 2. So we have, in red, we have a polynomial popping up, which might explain why the growth of the second one is larger. Now, if we do some basic algebra, we can express the general term of the Fibonacci sequence in the following shape. So we have a row vector times some matrix multiplication times a column vector, whereas for the involutions, I can do pretty much the same thing, but now instead of having a matrix which is constant, I have a matrix which changes one of the entries. So it goes 1, 2, 3, all the way up to n minus 1. I can view this as a matrix of polynomials, in which I can just plug in numbers. So the first sequence belongs to the class of C-finite sequences, whereas the second one belongs to the class of D-finite. And why am I talking about sequences and recurrences? Well, because we can obviously write programs which compute the general term, but we can also come up with automata which solve this task. And let's look again at the program that I had in the beginning. So I can have it in this form. I can actually write down the function that it computes. So on an input string W over the two-letter alphabet, it will output the length plus 1 factorial if the number of b's in the string is odd and 0 otherwise. Or I can reframe it as an automaton. So how would this look? This is the graphical representation, which is a bit inconvenient to work with if we want to analyze what it does. Or we can use like the more, algebraic representation. So a P-finite automaton is defined by three quantities. So the initial state, which is a row vector of constants, a transition matrix, a family of transition matrices, each corresponding to a letter. So for example, for the transition matrix of the letter A, I can have X times the identity, and this is a matrix of polynomials. And I have transition matrices for the other letters, and the final state vector, which is, again, a vector of polynomials. And how does the computation happen for this object? So basically, you take the initial state vector, you multiply it with the matrix corresponding to the first letter of the string, instantiated at 1, times the second matrix, instantiated at 2, times the third one, instantiated at 3. And you multiply by the final vector, instantiated at the next number, at 4 in this case. And if you do the computation in this case, it's exactly 24, which is what we would expect. So this type of automata generalized the finitely recursive sequences. If I were to have just constant entries in the matrices, then they would generalize the C recursive sequences like Fibonacci, and yeah, that also might explain the order of growth. Now I want to outline the main results of our work. So in the field of automata theory, like two important problems are the problem of equivalence, so deciding if two automata are computing the same function, and the exact learning problem in Angluin's framework. So I guess it's folklore the fact that for deterministic finite automata, the equivalence problem can be solved in polynomial time. Later in 1987, Angluin showed that the exact learning framework can be solved in polynomial time. Then Zheng in 1992 showed that for Q-weighted automata, so when the entries of the transition matrices are just rational numbers, so not polynomials, the equivalence problem is in polynomial time. Then in 1995, Angluin et al. Showed that, well, there is one type of automata for which we cannot solve the equivalence problem, the learning problem in polynomial time, and that is for non-deterministic finite automata under some cryptographic assumption. Then in 1999, Bimel et al. Showed that for Q-weighted automata, the exact learning problem is in P. And a bit more recently, in 2022, Van Hart et al. Showed that for Z-weighted automata, so when the entries in the matrices are integers, the exact learning problem is decidable. And what do we do in our paper? So first of all, we introduced this new type of automata, for which we showed that both the equivalence and the exact learning problem can be done in polynomial time. And we also showed that for Z-weighted automata, the learning problem can be solved in polynomial time. Now, I'll briefly outline the main ideas for each of these three results. So I'll start with the exact learning for Z-weighted automata. And the idea is to do a reduction from this problem to the problem of exact learning Q-weighted automata. And we still have access to these two oracles, the membership oracle and the equivalence oracle. And we use the algorithm for learning Q-weighted automata. If it tries to make a membership query, that is perfectly fine. It gives an input, and the oracle returns the integer output. However, the problem might occur when we're trying to access the equivalence oracle. And why is that? Because the equivalence oracle might complain about the fact that we are asking it if it's equivalent to something which is not a Z automata. So what do we do to fix this problem? We have a separate procedure which takes the hypothesis and decides if it can be represented as a Z-weighted automata. And in case it cannot, then, well, we have already found a counterexample which we can pass it back to the learning algorithm for Q-weighted automata. And if it is, then we pass this to the equivalence oracle. And it also does some sort of transformation. So it takes the hypothesis and makes it into the correct shape. And it can be seen as a constructive analog of Fatu's lemma, which basically says that if we have a sequence and the sequence has a recurrence with rational coefficients, but all the terms of the sequence are integers, then there is a recurrence just with integer coefficients. And then the equivalence oracle can either say, okay, yes, you found the target, in which case we halt, otherwise it returns the counterexample. Okay, so now going back to P-finite automata. For the equivalence problem, we are looking at backward reachable vectors. So these are basically the vectors that can be reached by well, kind of ignoring the initial state. So to be a bit more specific, for the empty string epsilon, the backward reachable vector is just the final state. And if we would have something like AAB. The backward reachable vector for that would be the matrix corresponding to the first letter, but evaluated at x now, not at any number, times the matrix corresponding to the second letter, evaluated at x plus 1, times the one for the third letter, evaluated at x plus 2, times the final vector, evaluated at x plus 3. And when we put all these vectors together, so the backward reachable vector for each possible word, and we take their span, we get something which is called the backward spacing. This is a very important object in the study of weighted automata. And yeah, the algorithm is basically a saturation algorithm. So what it does, it starts with the empty string, and it checks if the backward reachable vector for the empty string is in the span of everything that we have stored so far. For the empty string would be just the span of the empty set. Well, it's not. Then it will add one letter. So is the backward reachable vector for A in the span of the backward reachable vector for the empty string? If it is, it goes to the next letter, which would be B. It does the same thing for B. And then it adds one more letter to the left of B, and we continue on this path because for the backward reachable vector for B, it was not in the span of the previous vectors. And this keeps going until we're basically saturating. And why does this work? So it's very similar in spirit to the algorithm proposed by Tseng. And in that work, they use the fact that, well, if you have a sequence of vector spaces that are subspaces of q to the power n, then it will not run forever. It will not increase forever, and it can increase at most n times. And we use a similar idea, but now because we're working with polynomials, we have to use modules rather than vector spaces. And now the question is, okay, if I have a strictly increasing sequence of modules, for how long does it run? And the answer is, well, not for too long. And for this, we had to develop a technical lemma, which I'm not expecting you to read, but it says that, yeah, well, it's going to be polynomial in the desired parameters. Okay, and the last thing is the exact learning for P-finite automata. And this is the big picture. I'm going to take each of these parts separately and explain what everything means. We start by constructing the hypothesis automata. And to do so, we are using a set of access words, which are columns, and a set of test words, which are rows in a table. And this table is reminiscent of the Hankel matrix. And for example, the value at the intersection of row A and column BB would be the value of the function evaluated at ABB, which we can access using membership queries. And yeah, after we have this table, we can do some polynomial interpolation in order to construct the hypothesis automata. We then pass it to the teacher. The teacher says if we have learned the correct automata or not. If we have, then we halt. Otherwise, we add a contra-example. We get a contra-example, and what do we do with it? Well, we basically check on which is the first prefix on which the automata is wrong. And let's say that in this case it's correct on BA but not on BAB. We add BAB as a row to the table. And why do we do so? Because intuitively the rows in this table are what help us differentiate between states. So this is, if you want to make a comparison with Angluin's algorithm, these are the test words, and the columns give you the states. Okay, and yeah, so we would like to loop back and construct the hypothesis automata, but the danger is that, well, we might loop forever. What I haven't told you so far is that this partial learner makes an assumption about how many states the target automata has. And, well, using that, we are able to compute timeout. And if the table becomes too large, so if the number of table exceeds some timeout, which depends on the number of states and the maximum degree of the polynomial in the target automata that were guessed, then it means that we have the wrong choice. And the big algorithm, the only extra thing that we need to do here is to search for the correct values of n and d. And once the correct values of n and d are found, then we can guarantee that the partial learner will eventually output the correct hypothesis. Okay, thank you very much. And if you have any questions, I would be more than happy to take them.
Great, we have time for questions. Any questions from the audience? Yes, we have a question
there. Thank you for the talk. I was wondering if, for instance, someone wanted to apply this, if you can think about, for instance, the encyclopedia of integer sequences. You gave the example of the involution sequence. So maybe a somewhat unrealistic approach, unrealistic assumption of the model is that you can arbitrarily ask for a counterexample to your current model. But would it be practical to try and adapt this to, well, sequences that we can compute on the fly, but we can't really find an arbitrary counterexample? For instance, is there a bound on how many words you would have to check before you know whether your model is correct?
So let me make sure I understand your question. So you're basically asking me if if we know that the number of queries that we have to make is not too large.
Yes, essentially. Or for instance, you don't need an arbitrary one. You can view them in sequence, for instance.
So okay, in short, the answer is that, well, we can guarantee that the number of queries is polynomial. Everything runs in polynomial time. But what I mean by polynomial here, well, we do give some specific bounds in the paper. So that's one place where you can look exactly. But they are, yeah, it's basic. We're sometimes using arguments like, well, if you compose two polynomials, you get a polynomial. There are sources of improvements, and I think our intuition tells us that our bounds can be improved by a lot, but that's like future work.
Mm-hmm. Thank you.
Any other questions? Yeah, we have a question back there.
Thank you for the nice talk. I'm curious if there's an extension to Angluin's algorithm for alphabets, maybe infinite alphabets or symbolic.
No, so everything that we have here works only for finite alphabets, and the size of the alphabet actually appears in our bounds.
And what is the dependence on the size of the alphabet?
So I think it appears as, I don't know, the size alphabet raised to some power, which is a constant. So it's polynomial in the size of the alphabet. I'm not sure if it's not linear, but it's polynomial in the size of the alphabet.
Thank you.
Any other questions? I have a quick question. So in Angluin's algorithm, a subroutine is this equivalence check where you give it a proposal candidate, say DFA, and it'll give you a counterexample or tell you that they're equivalent. So in this setting that you're in now, what happens with this equivalence? It seems like this becomes maybe harder. Is this kind of factored out in your algorithm, or like, you know,
so
what happened there?
Basically, the reason why we started with the equivalence algorithm is because we want to make sure that the oracle that we assume we have access to can be run in polynomial time. And yeah, we have an algorithm which says, well, equivalence can be solved in polynomial time, so the oracle would basically.
Got it. So that's in there, and you've worked that out. Perfect. Yeah. I just missed that. Thank you. Any last minute questions? Oh. Well, I think with that, then we'll thank our speaker very much for the talk.
Thank you too.